In this video, I'm going to explain the motor effect. Let's start with the magnet. If I sprinkle iron filings around a magnet, it forms a pattern of lines. Here you can see the lines are forming, and these lines are called magnetic field lines. The region around a magnet is called a magnetic field. For A-level, you need to know that another magnet, a magnetic material, a moving charged particle, and a current carrying wire all feel a force in this magnetic field. Let's focus on the idea that a current carrying wire feels a force in a magnetic field. Here I have a circuit where the tinfoil is acting as a current carrying wire. It has been placed in a magnetic field. Here is the North Pole and the South Pole. Let's see what happens when the current flows. When I press the switch, a current will flow through the circuit. The tinfoil moves upwards. What happens if we change the direction of the current? This time, the tinfoil moves down. The direction in which the current carrying wire moves can be determined using Fleming's left-hand rule. When we use Fleming's left-hand rule, we use our thumb and the first and second fingers of our left hand. You need to hold your hand like this, with your thumb and your fingers perpendicular to each other. It helps if you write F, B, I on your fingers. F is the force, B is the magnetic field, and I is the conventional current. Then all you do is point your fingers in the direction of the magnetic field and current to find the direction of the force. Let's look at the direction in which the force on the current carrying wire acts. The conventional current acts in this direction. The magnetic field acts from north to south, so it goes in this direction. We can use Fleming's left-hand rule. The current is travelling this way. The magnetic field is pointing this way, so then the force acts upwards. Let's see what happens if we change the current the other way round. So the conventional current is going this way. The magnetic field is still acting from north to south in this direction. So if we use Fleming's left-hand rule, we can see that the conventional current is this way. The magnetic field is still pointing north to south this way, so we can see that the force acts down. Let's see how what we have learned can help us explain the motor effect. Here is a motor, it has a magnetic field and a current carrying wire. We're going to pass a current through the wire, going along this direction on this side and this direction on this side. Let's work out the direction of the force on each side of the wire. Let's use Fleming's left-hand rule to see what happens to this wire in this magnetic field. As you can see, the magnetic field acts from north to south, so points in this direction. The conventional current on this side of the wire is acting this way, so our finger goes this way, and we can see that the force acts downwards. On this side of the wire, the magnetic field still acts in this direction. However, the conventional current is acting this way, so our finger stays this way, and we can see that the force is upwards. Therefore, the wire is going to rotate continuously this way, and this is known as the motor effect.